Hi again. So today we'll see how to apply t-test on a sample data. Definition of t-test and its details have already been covered in the theoretical part, but I will again share the definition now. So a t-test is a type of inferential statistic used to determine if there is a significant difference between the means of two groups, which may be related in certain features. So t-test can be applied on a single sample data, paired samples and unpaired samples. In this session, we'll only cover the paired and unpaired group of data. Okay. Let me show you what the data is. So let's say we have some kind of treatment given to some students, and then there was a test conducted prior to this treatment and a test conducted after the treatment. So the score prior to the treatment is pre-score and the score after the treatment is post-score. Let's create a hypothesis out of this example. So for paired t-test, I have created this hypothesis. There is no mean difference between the pre and post scores of students, while the alternative hypothesis would be there is a significant difference between the pre and post scores of the students. This is a paired t-test because the same sample is being used before and after the treatment, and we are just trying to find out the impact of a treatment on the same subjects. Now you can see the assumptions of paired and unpaired t-test on your screen. The unpaired sample t-test is actually called two independent sample t-test. Two samples could be considered independent if the selection of individuals or objects that make up one sample does not influence the selection of individuals or subjects in other sample in any way. So in independent sample t-test, the measurement of one sample have no bearing on the measurements in other sample. Okay. We would again use p-value to decide whether to accept or reject the null hypothesis. Let me also show you the data for paired and independent t-test. Please notice the difference between the two. Here we have two samples in two columns. For example, pre-scores in one column and post-score in one column. If you have this type of CSV file, we need to apply t-test in a different way. While if you have a CSV file in this way, where let's say the group comprises of boys and girls, B denotes boy, G girls, and now you have scores here, and in our independent sample t-test we would like to find out whether there is a significant difference between boys and girls scores. Okay, but just try to see the difference here. The score is in one column. It's not that we have score for B here and G here. Okay, like for example, now if you see, if it would have been in this way, this would be similar to what we have in paired test, but we don't have scores for boys and girls in different columns. We have everything in single column. So I am just trying to show you the difference, because the way we apply t-test depends upon how the data is structured. I'll show you in R Studio in a while. So let's try to apply the paired sample t-test in R for pre and post scores. So here is the hypothesis: there is no difference between pre and post scores of students, and then alternative hypothesis: there is significant difference between pre and post scores. Now alternate hypothesis could be mean post score is not equal to mean pre score. That would be a non-directional hypothesis. But let's say if we want to prove or find out that the mean of the post score is greater than mean of the pre score, that means we are trying to say that our treatment has a significant impact. Okay, in that case we need to have a single tailed hypothesis. When we say mean post score is not equal to mean pre score, is a two tailed hypothesis. But in this case we are using a single tailed hypothesis, because I just want to show you how to create a single tailed hypothesis in R. Okay, so our alternate hypothesis is not that pre and post score are equal, but mean post score is greater than mean pre score. Okay, let's set the working directory in R. Read the data from CSV file. Let's see the structure. There are 3 columns in it, but we just want pre and post score to conduct our t-test. Let's again see the structure of the data. Now we just have 2 columns. So let's see the assumptions for t-test. Here are the assumptions. The dependent variable must be continuous. So what is a dependent variable here? The dependent variable is a score, and the independent variables are the situation prior to treatment and the situation after treatment. So you can say pre and post are independent variables, while the dependent variable is the score. The score is a continuous variable. So our first assumption is met. Observations are independent of one another, which is also true. The dependent variable should be approximately be normally distributed. So as I told you earlier, how to check the normality of a data. Okay, so it's 0.01. So the p-value is less than 0.05. We need to reject null hypothesis and accept alternate hypothesis. Data may not be normal, but again I'm not going to show you how the data can be converted to normal, but it can be transformed to a normal data. I'm going to continue to apply t-test. Prior to that, you can also find the mean scores of the pre and post scores. Mean for post. Mean of post score is higher than mean of pre scores. Now let's apply the t-test. Now here you see how we are trying to apply t-test. So there are 2 groups, post and pre. Post minus pre is greater than 0. Please remember that this greater means your variable 1 minus variable 2 is greater than 0. If you were trying to test an alternative hypothesis, which was pre-mean score is greater than post-mean score, you should have kept pre as first place and the post at second place. But here our alternate hypothesis is post-mean score is greater than pre-mean score. So we need to keep post at first place and pre at second place. This is what it is all about, the first 3 parameters. Okay, then paired is equal to true because we are running a paired sampled t-test. Just click enter. Now you can see the result. Here is the result. So t value, degree of freedoms, I think there were 40 odd values in our CSV. So 39 is degree of freedom, and then 0.08. It is slightly above 0.05. That means we cannot reject the null hypothesis. We have to accept the null hypothesis, which says there is no difference between pre and post scores of students, and the mean difference is 0.975. Okay, let us apply the 2 independent sample t-test now. You can see the data here. As I shown you earlier, this data has the following form. Column 1, which is a student column, this contains boys and girls, and column 2, which is score, this contains the scores for boys and girls in the class. These are the assumptions for 2 independent sample t-test. The scores for boys and girls should be normally distributed, and then variance for these 2 groups of boys and girls should be equal. Let's see how to apply this in R. Let's read the CSV file. The working directory is still the same, so I am just reading the CSV file. Let's see the structure of the data frame. So we got two columns. Now, if we want to check the normality, we'll use the same Shapiro-Wilk test as we have been using in our last analysis examples. There can be two ways of finding the normality of scores for boys and girls. So we need to fetch the scores of the boys and then find the normality of the same. So one way of doing this is, let's say we create a data frame. This is another data frame which fetches the records where a student column is B. Okay. Now you can apply the Shapiro test on the score column of new data frame DFB. It's more than 0.05, so we cannot reject null hypothesis, and the null hypothesis is data is normal. Okay. Similarly, you can do for the score for girls. Okay. If you want to see what was there in DFB data frame, you can do like this, or you just write DFB and see that all the records belong to boys because we selected the scores for boys in this data frame. Okay. Another way of applying Shapiro test without creating a new data frame for boys and girls is like this. So with DF is the original data frame in which we read the CSV file. Shapiro test score student is equal to B. So it would apply Shapiro test to the score column where student is equal to B. So we'll be able to know if the scores are normal for boys. This is how we were able to know the normality of the data for scores for the boys group. Now let's see the next assumption. Next assumption is variance for two groups are equal. This means the score for boys and girls have equal variance. We would apply another test to find the variances of these two groups. Okay. So basically this is an F test and it tests the variance for scores with respect to student column which contains the group boys and girls for the data frame DF. It provides us F statistics, the degree of freedom for boys and degree of freedom for girls, and p-value. Now p-value is 0.2891. So the null hypothesis in this case is variances are equal. And alternative hypothesis is variance of two groups are not equal. In this case, the p-value is 0.2891, which is more than 0.05. This means we have to accept the null hypothesis, which says the variance of two groups are equal. Okay, and that 95% confidence interval are shown below. Okay. Now, as both the variance are equal, we can continue and apply the t-test. Gives the output. If variances are not equal, even then we can apply the same. When I am saying variances are not equal, then this assumption is not met. Still, if we apply the t-test, R applies a different flavor of t-test, which is called Welch t-test, which is similar to t-test, but it is applied only when variances are not equal. So in this case, I have put variance dot equal is equal to false. And now if you run this, you will see it is applied Welch two sample t-test. And if you have noticed earlier, it was just two sample t-test because variance were
put equal in first case and false in second case. You also need to note that we are not putting any alternate hypothesis here. Till the time we don't put an alternate hypothesis here, by default it is two-sided. If we want to put it, we can put it two-sided, greater or less. So if we are not putting, by default it would be two-sided.
So let's give some time to understand how to frame alternative hypothesis for different type of structures that we have. As I showed you earlier, there are two different structures that I have. For paired sample t-test, I had a structure like this, while independent sample t-test, I had a structure like this. Okay, I tried to explain the difference earlier, but now I'll try to make it more clear with the help of this document. So if you see here the pre and post scores, these are the categories of independent variables. So our independent variable was treatment, and the dependent variable was the score. And the treatment had two categories, before the treatment and after the treatment. So these two columns are the categories of a independent variable. If you notice this structure, we have the categories of independent variable in single column and the score here. Okay, so the student is independent variable and these are the categories. Now, what difference does it make in creating a alternative hypothesis? In R, this makes a lot of difference because we need to understand very carefully how would we create a alternative hypothesis. Now, null hypothesis is very simple, which says the mean of pre and post scores are equal. But alternative hypothesis may be trickier.
If we want to create an alternative hypothesis which says the mean scores are not equal, it is very simple because by default, if you don't mention any alternative hypothesis in R, it would consider as two-sided. Okay, and this is not equal to it. It's very simple. But if we want to create a hypothesis which says pre-scores are greater than post-scores or vice versa, so you need to follow a sequence in this command to have such hypothesis. Okay, let's say this is variable 1 or category 1 and this is category 2. So basically the keyword here comes as a result of the scores of category 1 minus category 2. Okay, it cannot be category 2 minus category 1. Whichever is mentioned earlier is considered as category 1. Whichever is mentioned later is considered as category 2. Now, if you want to have pre as category 1, you should mention it here. Okay, and then post become category 2. Minimum will be the category variable mentioned first and the subtrahend would be category or variable mentioned at second place in sequence. So it will be category 1 minus category 2. Now you can mention whatever you want to mention here. You want to mention pre is less than post, you mention less here. You mention pre is greater than post, you mention greater here. This is how the keywords in alternative is defined in R for the structure like this. Now, what would happen if you have structure like this? Here, the categories of independent variable are mentioned in single column. There are two groups, let's say boy and girl. It may be man or women, but you need to find out which group starts with a letter which comes earlier in alphabet. So B comes earlier than G. In this case, M comes earlier than women. So your alternative hypothesis would be based on these letters, the starting letter of the two groups. Now, whichever letter come earlier, that group would be minuend, and whichever letter comes later would be a subtrahend. Okay, so boy will be minuend in this case, and women will be subtrahend in this case. So your alternative hypothesis would be formed as mean score of boy minus mean score of girl is greater than 0 or less than 0. The text in red, this is not the right way to form alternative hypothesis. The text in green, this is the right way in this case to form a correct alternative hypothesis. So either you want to prove that the score of boys is greater than girl, then you can put greater here. If you want to prove or find the mean score of boys is less than girl, you can put lesser here. But it would be boy minus girl, not girl minus boy. Just because B comes earlier in alphabet than G, and it would apply to this example as well. And maybe if there was, for example, colors black, white, so it would be B minus W or something else. But it will always depend upon the first letter of the groups. Okay, this is how we form alternative hypothesis in R. So if I click enter here, so this is an alternative hypothesis where we say the mean score of boys minus mean score of girls is less than 0, or mean score of boys is less than mean score of girls. Okay, let's put and see. So the p-value here comes 0.03, which is less than 0.05. So that means we can reject null hypothesis in favor of alternative hypothesis, which says the mean score of boys is less than mean score of girls. Okay. So this is how you can run the paired and independent sample t-test. I explained to you all the assumptions, how to create alternative hypothesis in R for various kind of structures that you may get in the data.